Okay, so last class we just finished up with the quiz. You guys have that now. So let's take a look now. What we're going to do is start looking at these trig functions. And we've mentioned that they're all about the circle. And we've seen those parts of a circle. And the most important parts we're going to look at, of course, we have a reference diameter. Remember, a diameter is just a chord that goes through the center of the circle. And that reference diameter is usually horizontal. There are times where we change our frame of reference, and we'll discuss that a little bit as we go on. And we use a vertical diameter for the reference diameter. But the standard reference diameter is the horizontal. And we talked about something called a sine. And a sine is actually a distance. It's a quality of each point on the circle. Like this point on the circle has a sine, and that is its sine. So from that point to that reference diameter. And distances are always measured at a right angle like that. So that is the sine of that point. This point has a bigger sine because it's further away from that reference diameter. So that length is the sine of that point. And obviously that length is the sine of that point, and so on. We talked about a secant. A secant, remember, we said it was a chord extended outside of the circle. The technical definition of a secant is a segment or a line that contains points that are both inside and outside of the circle. And then we had the tangent. A tangent touches without ever entering the circle. So again, that tangent shares exactly one point with the circle. So now what we're going to be looking at is we're using a structure called a unit circle. Is he okay? A unit circle is a circle with a radius of 1 unit. So pretend that looks like a circle. You have to do a lot of pretending. We're going to put our reference diameter across there. Let me try that again. Get it closer to what would be the center there. So there's a reference diameter across that circle. Kind of like the compass rose on a map. We think of this being east, north, west, and south. Well, navigationally, we consider this to be 0 degrees. We talked about that when we were looking at angles. So that is defined to be what we would call the initial side. All angles start there. Now I'm going to draw in, just for reference here, the vertical axis. Pretend that looks straight. And then all angles they go counterclockwise around this. So 90 degrees would be at the north direction, and 180 would be at west, 270 at south, and 360 back at east. If I have an angle, let's say it goes this far. That's about a 50, 55 degree angle. I'm going to mark that angle with the variable theta. That looks like that. It's just a Greek letter theta. We use it to represent generic angles. That green line there is what's called the terminal side of the angle. I'm actually move it just a little bit so we don't have issues here. So that is called the terminal side of the angle. That's where the angle ends or stops. Well, that terminal side, of course, maps out a point on the circle right there. That point gives us the trig functions of that angle. Remember, a sine is the distance from that point down to that reference diameter. That right there is the sine of our angle theta. A secant contains points both inside and outside of the circle. So if we take that terminal side and extend it outside the circle, it forms a secant. Well, how far do we have to extend it? That's where the tangent comes in. The tangent is tangent at that reference diameter, and it continues up until it intersects or hits the secant. So this length here is the secant of theta. And this length here is the tangent of that angle theta. Now, one thing you will notice here, this is a unit circle with a radius equal to 1. So this length right here is 1. So what that's telling us is that the length of the sine right here can never be larger than 1. Because even if this angle were right here at 90 degrees, the sine would be that length right down there, which is going to be 1, because it's the radius of the circle. So sine, and of course if it were down here, it would be a negative 1. So sine has to be between negative 1 and 1, because of the way this circle is constructed. So it's greater than or equal to negative 1, less than or equal to positive 1 for sine. The secant, because of the way it's constructed here, is always longer. It always continues past the radius outside of the circle. So the secant is always greater than or equal to 1. Or the secant is less than or equal to a negative 1. Because, of course, if it's going in other directions, it can be considered negative 1. The tangent can be anything. If my angle were down here, you can see tangent's almost 0. It's really small. If my angle were up here, you can see tangent would go way up off the screen up there. So tangent can be anything from negative infinity to positive infinity. There's no restrictions on the tangent. The only restrictions on tangent come when we start looking at some of our identities. These are the 3 trig functions: sine, secant, and tangent. Well, it could be 0, it could be positive infinity, or it could go down here and be negative.
Okay, but I'm saying if the line that you draw there
starts at the, yep, always starts at the reference diameter. So, yep, it either start from here or over here.
So if you have a 90-degree angle there, how do you connect it with the secant?
Good question. At 90 degrees, both the secant and the tangent are infinitely large, so we call them undefined at that point. It's a very good question. If that angle is 90 degrees, the secant going up here would go straight up. The tangent going up here would go straight up. They would never connect. At 89 degrees, they connect way up there. Both the tangent and the secant are extremely large at 89 degrees. At 90 degrees, they cease to exist because they'll never intersect. Now, those of you that have done trig before and used trig before might be looking at that saying, the sine looks familiar, the tangent looks familiar, but the secant not so much. What do we typically use in place of the secant? Close, cosine. What is cosine? There's cosine, cosecant, and cotangent. Well, the key to understanding those is this prefix, CO. That literally is talking about a sine that has the prefix CO on the front. And that prefix CO means of the complement or complementary. So the cosine is asking, what is the sine of the complement of this angle? So let's take a look at that. Here's a unit circle. And I'm just going to put an angle on here and I'm going to name it. So I'm going to say this is 35 degrees here. Its sine is this distance right here. That's its sine. Abbreviated SIN for sine. Where is the complementary angle? Well, the complementary angle, the cosine is the sine of the complement. Well, the angle that's complementary to it would be right here. That's 55 degrees. The sine of 55, I could flip it around, or I can just change my reference diameter to be the vertical diameter. This distance here would be the sine of 55 degrees. Or the cosine of 35 degrees, the sine of its complement. Does this make sense? So if I tell you that the sine of 30 degrees is 0.5, the cosine of 60 degrees has to be 0.5. Why? Because 30 and 60 are complements. They add up to 90. Since they are complements, the sine of one has to equal the cosine of the other. The cosine of 60 equals the sine of its complement, and its complement is 30. If I tell you that the sine of 60 degrees is 0.866, the cosine of 60 degrees, or it's not 60, the cosine of 30 degrees has to be 0.866. Nope. The angles are the complements, is the important part. The sine of 1 is equal to the cosine of its complement. So the sine of 30 is 0.5. The complement of 30 is 60, so the cosine of 60 is also 0.5.
Okay, so that on the bottom of the sine of 30 would be
0.5. Okay, good. I see where you're going here. Shouldn't they add up to 1?
Yeah.
No.
No.
Kind of, but not quite. It's what we call a Pythagorean relationship. If you look at the triangle here, this distance here is basically the cosine of 35. I'm just taking this distance and moving it down. And what you see there is they form a right triangle, where this side of the right triangle is 1. It's the radius of 1. It's a unit triangle. If I let this be A and B, A squared plus B squared equals C squared. Well, sine of 35 degrees squared plus cosine of 35 degrees squared has to equal 1 squared, which is just 1. So for any angle, not just 35 degrees, but any angle, that relationship has to be true. So sine of 30 degrees is 0.5. Sine of, or cosine of 30 degrees is 0.866. I gave you the same angle, so they're not, the function doesn't have the same value. Sine of 30 squared, so 0.5 squared, plus cosine of 30 squared, 0.866 squared, has to equal 1 squared, or just 1. 0.5 squared is 0.25. 0.866 squared is 0.75. That adds up to 1. So it's not quite, you're thinking the right idea that they have to add up, but it's their squares that have to add up, not the value of the function itself. Now, of course, we could define cosecant and everything off of here now. If I extend this out and I intersect it with the tangent from this point, from that axis, this is the cosecant, that's the secant of the complement, and this, of course, is the cotangent, the tangent of the complement. We're not going to be so concerned with those because we're going to define them in other ways here coming up. But so what I want to do now is I want to look at a right triangle. How did this stuff get from the circle to a right triangle? Well, here's a right triangle. And let's say we were looking at this angle here. I'm going to call that angle theta. A right triangle has 3 parts. It has 2 legs and a hypotenuse. Well, the hypotenuse is the side that is across from the right angle. It does not touch the right angle. Always the longest side of the right triangle. The legs, of course, are the other 2 sides. we break those legs down in what's called the adjacent side, or the adjacent leg. The adjacent leg touches the angle that we're looking at. So if we're looking at theta right here, that's the adjacent leg. And then the opposite leg. So the opposite leg, it still touches the right angle, but does not touch the angle that we're looking at. So if we switched to looking at this angle up here, those two would have to switch spots. This would become the opposite, and this would become the adjacent. Does that make sense? So the opposite and adjacent depend on which of those two non-right angles we're looking at the time. For right now, we're going to be looking at this one right here. Putting our unit circle up here, next to this triangle. If I put this angle theta right here, which is the same as this angle theta, I draw in my sine to complete the right triangle. These two triangles have to be similar because the right angles are obviously the same, and these two angles are the same. So the third angle must be the same. And if those triangles are similar, we've talked about how corresponding sides have to form that proportion. Well, let's look over here now. This is the sine of theta here. This distance down here is the cosine of theta. And of course, this length is 1. That's the radius of my circle. So if I want to compare these two triangles, let's say I want to look at the cosine. Let's look at the sine first. Let's say I want to look at the sine. I'm going to look at the sine, and I'm going to compare it to what side of the other triangle corresponds to the sine. That'd be the opposite side here, right? Those are both the vertical side. I'm just going to abbreviate it OPP. I'm also going to use the side that we know here, the 1, for the hypotenuse. What part of this triangle corresponds to that 1? Well, the hypotenuse. So when we're looking at a right triangle, the value of the sine of that angle is the ratio of the opposite side, length of the opposite side to the length of the hypotenuse. If we look at the cosine now, what side of this triangle over here corresponds to the cosine? Yeah, the bottom side, the adjacent. So I'm just going to abbreviate that ADJ. And I'm going to use the 1 again, and the 1 still corresponds to the hypotenuse. So the cosine of the angle is defined to be the same as the adjacent side divided, the length of the adjacent side divided by the length of the hypotenuse. So that's where those trig functions have now been transferred from the unit circle to right triangles. Now let's draw in a slightly different triangle over here on the unit circle. I'm going to extend this and this here. So now what I have here, this is the tangent of theta, and this side is the secant of theta. And now it's this length from here to here that's 1. That's the radius of the circle all the way out there. So if I look at the tangent of theta, what side of the other side of the triangle corresponds to the tangent? Opposite. This time 1 is down here, so I'm going to use the 1. Now what side of this triangle corresponds to the 1? The adjacent. So the tangent of an angle, oops, that didn't work with crap. The tangent of an angle is equal to the ratio of the length of the opposite side divided by the length of the adjacent side. And finally, I can put up the secant. The secant of an angle is this side here, which corresponds to the hypotenuse. And we're going to use the 1 again which still corresponds to the adjacent side. So the value of the secant from the unit circle is equal to the ratio of the length of the hypotenuse divided by the length of the adjacent side in the right triangle. So we can define from that right triangle, we can define the value of those trig functions as ratios of sides. We don't have to look at the unit circle anymore. Because realistically on the unit circle, how are we going to measure those lengths to find the sine, cosine, and stuff anyway? So, where this is theta, that's my hypotenuse, opposite and adjacent. As we said, the sine of the angle is the length of the opposite side divided by the length of the hypotenuse. I would recommend making this in a list somewhere, maybe the back of your notebook or something, so you have it to reference to real quickly, because you're going to use these definitions a lot over the next several weeks. The cosine of an angle is equal to the ratio of the length of the adjacent side divided by the length of the hypotenuse. And the tangent of an angle is equal to the length of the opposite side divided by the length of the adjacent side. We just saw here that the secant of an angle is equal to the length of the hypotenuse divided by the length of the adjacent side. If we were to keep going, the cosecant, abbreviated CSC, stands for cosecant. Similarly, I could do the same type of thing and find that that is the length of the hypotenuse divided by the length of the opposite side. And the cotangent is going to be the length of the adjacent side divided by the length of the opposite side. As I look at these, I see some relationships that stick out. One of them is right here. The cosine and the secant. Remember a little while ago we said sine, secant, and tangent are the three main trig functions. But on your calculator it's sine, cosine, and tangent. They put the cosine in instead of the secant. And here's why. Cosine and secant involve the same two sides of the triangle. They both involve the adjacent side and the hypotenuse. It's just the reciprocals. In fact, the secant is the reciprocal of the cosine. A similar relationship exists between the sine and the cosecant. The cosecant is the reciprocal of the sine. And then the simple one, now that one's hard to remember because it's cosecant and sine, and it's secant and cosine. It seems backwards. That's the way they link up. This one makes sense. The tangent and cotangent are together. The cotangent is actually the reciprocal of the tangent. So, how are we going to calculate these values? Well, if I give you a triangle, you can find them. Sure. This, by the way, like I said, is the big page that you want to have so you can use it later. We're going to reference those functions a lot. We're going to look at finding secants, cosecants, and cotangents. But these three here, again, we're going to use those definitions a ton over the next 6 weeks. So if I have a right triangle here, right angle there, and I give you that this is angle A, angle B, of course, we almost always make the right angle angle C. And let's say this is going to be 5, 12, and 13. What is the sine of angle A? Remember, sine is opposite over hypotenuse, right? So from angle A, what's the opposite side? 5. What's the hypotenuse? 13. 13 is going to be the hypotenuse no matter what. What is the cosine of angle A? Perfect. Cosine is the adjacent side, which is 12 over the hypotenuse, which is still 13. What's the tangent of angle A? 5 over 12. Good. Opposite, which is 5, adjacent is 12. What's the cosine of angle B? Now we're looking, this is angle B here. Cosine is adjacent over hypotenuse. If this is angle B, which side is adjacent to it? The 5 is next to it. It touches that angle. Remember I said when we switch angles, the adjacent and opposite sides switch spots. So this is now the adjacent side if I'm looking at angle B here. So it's 5 over the hypotenuse is 13. Notice, no, cosine is what I'm looking at, not cosecant. Cosine. Notice the sine of angle A and the cosine of angle B give me the same fraction. Well, what's the relationship between angle A and angle B here? What do they have to add up to? Because a triangle has 180 degrees. If this angle is 90, those two have to add up to the other 90. So A and B are complements. So it makes sense the sine of A is equal to the cosine of B because A and B are complements. The sine then of angle B is going to be, well, from angle B, what's the opposite side? 12 over the hypotenuse of 13. Again, the sine of B equals the cosine of A because they're complements. Now the tangent of angle B, it's opposite over adjacent. So from B, the opposite is 12, the adjacent is 5. Now let's bring in those other functions, the secant. Secant of A. Secant, remember, was hypotenuse over adjacent. So the hypotenuse is the 13. If I'm looking at angle A, which one's adjacent? The 12. The cosecant of angle A is hypotenuse over opposite. So it's still the 13, and the opposite side is the 5. Cotangent of angle A, it's still adjacent over opposite. So the adjacent side is the 12, and the opposite side is the 5. By the way, tangent of B equals the cotangent of A because they're complements. The secant of A is the reciprocal of the cosine of A. Cosine's 12 over 13, secant's 13 over 12, the reciprocal. So there are a lot of relationships like that that we're going to run into. On your calculator, if I want to find the sine of 30 degrees, all of you, it looks like, have a two-function calculator. So you would just hit the sine key first, type in 30, and hit equals. It should give you 0.5. If it does not give you 0.5, let me know, because that means you're stuck in radian mode instead of degree mode. Everybody got 0.5? Okay. Cosine of 30. Same thing. Hit the cosine key, type in 30, better give you 0.866. Tangent of 30? 0.577. Good. That's where the easy part ends. If you're asked to find the secant of 30 degrees. Now remember, secant is 1 over the cosine. So there's two ways we go about this. We do 1 divided by cosine 30, which would work. 1 divided by, press the cosine, and then 30 degrees and hit equals. Should give us, what, 1.15? Is that right? 1 divided by cosine 30. 1.155, yeah. The other way to do it, and this is the way I'm going to ask you to try to do it if you can make it work, is we know secant is linked to cosine. All of you have a key on your calculator that looks like that, x negative 1. That's going to be totally different. No, that's totally different. We just want the x negative 1 key. Yours might have a 1 over x key instead. Those are the reciprocal keys. So here's the way we're going to enter that. You're going to type in cosine of 30, and you're going to close, don't hit equals. You're going to close the parentheses, and then you're going to hit that reciprocal key. 1.155. Good. The reason we're doing it this way is because when we go to do inverse functions later, we're going to use a similar thing. That key is going to be just put in a different spot is all. So now if I want to do the cosecant of 30 degrees, what trig function goes with cosecant? It's the reciprocal of sine. So what we're going to do is this. You're going to type sine 30, close your parentheses, and then hit that x negative 1 key, then equals. 2 is exactly the cosecant of 30 degrees. Remember, domain error. So clear it out. Hit the sine key. Okay. Perfect. And then the cotangent of 30, remember that is the reciprocal of the tangent. So what we're going to do there, come back here, is we're going to do tangent 30, and then that close the parentheses, and then that x negative 1 key. Perfect, 1.732. So let's do sine of 60 degrees. Type that in, tell me what you get. .866. Perfect. Cosine of 60 degrees. 0.5 is perfect. Sorry. Come on. Tangent is 1.732. Good. Secant of 60 degrees. Something's off there. You're going to do the cosine of 60, close it, and then do the x negative 1. Gives you 2. Yeah, remember, you got to remember, secant is linked with cosine. That's a big one. That's hard to remember because, yeah, you're right. It seems it would make more sense if secant was linked with sine, but it's not. The cosecant of 60 is then going to be found by using sine 60. Close the parentheses and the x negative 1. 1.155. Perfect. And then the cotangent of 60 is going to be found using the tangent. You got it. That's another page you might want to have down right there, so that you know what buttons to use to calculate each function. Unfortunately, I'm on page like 17 right now because I have all my other classes for the day on the same document.
No, I'll wait till we get this one, but I don't want
I've-
to email phone in here, 'cause I can't keep up on.
I've got to be here for another couple hours anyway, so I'll make sure this is posted before I leave. Okay, so our homework for tonight is not in the packet that I gave you. It's actually going to be on another worksheet I'm going to hand out here. Page 345 through 346, 1 through 37, the odd. And let me get back here. His head's in all your pictures.
Most of them. Top of his head.
Never gonna fix face mine.
No, they're all getting deleted as last day of
It's gonna be
school.
all
Alright.
in his nose.
Don't worry, they'll all get deleted. I don't even have any of my notes from first semester anymore.
I'll keep mine forever, mine's beautiful.
Cut you kind of short on work time today, but I'll let you have the last 6 minutes to get started.